Okay. Okay. All right. So this is the bread and butter part of the second phase of the course. So as I said in a number of the videos, the course is divided into 3 groups. The sort of the definition of digital, binary, number bases, binary things, kind of switching algebra and the basic theorems, the canonical forms of SOP and POS. That's kind of phase 1, codes, and how we represent things in binary. Okay, part 1, that was the first test. Second test is combinational design, and we finished that, and we even threw in the flip-flops at the end, which really are sequential devices. And then the last part of the course, which we start on Monday, is going to be the sequential design, and that's where we're going to look at state machines, basically. Okay, so when it comes to combinational design, it is fundamentally and essentially looking at a truth table and translating that truth table into a K-map. And then we study K-maps because K-maps are the best way to simplify an expression. Now, if you're having trouble looking at a K-map and writing down the minimal SOP expression or the minimal POS expression, you need to work on that, because if you can't do that, you're going to do poorly on the test. That's one of the things the test is about. So let's just go through this, and we'll do both the POS, and we'll also do the SOP form of the solution. So we'll do that too. Okay, so I'm gonna switch over here, which is a different. That's the one I thought. Okay, I guess I gotta have a different one. That's fine. Maybe I'll switch it out. I guess it could be this one. No, this one. No. All right, it must be this one. Yeah. Okay. So this is I'll do the one that we're actually looking at over here. All right. So let me change screens then. Okay. So now you should be able to see this over here. Can you see my hand, everybody?
Yes.
Okay. So this is the one you were just looking at, but now it's down here instead. All right. And I'm gonna put on some glasses so I can see better. Okay. So the first thing I'm going to do is I'm going to put this truth table in. Now, you should be way past this, but just for sake of completeness, this box corresponds. So you can number the rows, 0, 1. Hang on one second. Let me just get my phone. Okay. All right. Of course, it was a sales call of some kind. Okay. And let me get my other pair of glasses too. Okay, this will be better. Okay. So you can number the rows. Now, if you look at the rows, just look at the binary value. So this is 0, 1, 1, 1. So obviously that's row 7, because that's the binary value. 1, 0, 0, that's 8. So you just look at the numbers. 1, 1, 1, 1, that's F, okay? So you don't really even have to number the rows, because you can read the binary numbers, the 4-bit binary numbers right off this. And remember, I told you right at the very beginning, memorize all 4-bit combinations from 0, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. You should know those cold. Okay, but just for sake of completeness, 0, 1. Now notice this is not 2. 2 is down here, and 3 is there. And the same thing here, 4, 5, 6, and 7. Notice 6 and 7 are switched. And now notice that 8 and 12 are switched. This is 8 and this is 12 instead of 8 and 12, right? 8, 9, 10's down here, 11, 12, 13, 14, and here is box 15. That is the high order box right there. Low order box, high order box. All right. So you should always keep in mind that that's how we number these things. And then you have to put the ones in. So I put a 1 here because there's a 1 and a 0. Then there's a 0. Then there's a 1. Well, that goes down here because that's 2. Then there's 3 is a 1. But 1 was a 0. I'm not going to put in the 0. Okay. But I will put it in down here where I'm going to kind of keep track of the zeros. Okay. 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, and finally 0, 0, 1, 1, 0, 0, 1, 1. And then I'll put in all the zeros down here. Okay, so I put in that 0, then there's a 0 here and a 0 here and a 0 down there. And then there are 2 zeros here. And then there's a 0 here. Now I count them just to make sure I didn't mess it up. 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7, 8, 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. There aren't any don't cares in this problem. Okay. So this is the first part. You've got to be able to copy the data from the truth table into K-maps. And then you have to be able to look at the K-maps. Now, it's easy to make mistakes on the K-maps. It's really easy to make a mistake. So I'm going to put on the speaker and take off the headphones. Okay. All right. So the first thing I notice, I have a 1 in every corner. So I can do the 4 corners here. That's a tricky one. Don't screw that one up. Then I notice I have a whole row here. And then I notice I have a group of 4. Now, how many of these are essential? How many are non-essential? And what do I have? Now, are there any others? Yeah, so you probably can do, yeah, you probably can do this one. This one is a little tricky, where you loop these 2 ones with those 2 ones. And it turns out a consensus term. So, but obviously that's not necessary. And that's about the only other one. There's really nothing else. Okay, so we have the group of 4, all corners, the group of 4, this row, the group of 4, this circle here, and the group of 4 wraparound. So we have 4 groups of 4. Now, clearly, this last group of 4 we don't need because these 2 ones are covered by other boxes. The 4 corners covers this one, and the row and this group covers this one. This one's covered by 2, this one's covered by 2. But this one right here, well, this one's covered by 2, but this one right there is only covered by 1. This one right there is only covered by this row of 4. And these 2 ones up here are only covered by the 4 corners. So those 3 are essential. So what we have is, we have 3 essential prime implicants, 1 non-essential. We have 4 prime implicants, and our final SOP expression we can write. So I'm going to write the SOP expression down here. Put it on the bottom. Okay, so first I know the 4 corners is, for a 4 variable problem, is B prime, D prime. Plus, I know this row is CD, CD, and then I know that this group of 4 here is A, C. Okay, and then this wraparound group is B prime C, but we don't really need it. I'll mark it here, B prime C. We don't need it because we covered all the ones with these three two variable terms made up of groups of 4 boxes each. All right, that's the SOP expression. Now let's look at the POS. So the POS looks like this group of 4, this group of 4, and this wraparound group of 2. So now how do I write the SOP terms? I mean, sorry, how do I write the max terms, which turn into the POS expression? Well, I can do it a lot of different ways, but the way I prefer to do it is I prefer to pretend they're ones, write what it would be if they were ones, and then invert it, and that gives me the correct max term. Now, having said that, let me just make crystal clear. The POS solution is not the inverse of the SOP. Now, let's look at this. The SOP solution was B prime D prime plus CD plus AC. Okay, let's invert that. All right, that gives us, we take this in, and that would give us B prime D prime inverted times CD inverted times AC inverted. And then if we take the one into here, so we change the pluses into times, but we just inverted these as groups. But if we take the inversion in, so this would actually be a NAND term here. So this would be in yeah, well, anyway. So now I'm going to take this in, and now I get B plus D quantity times C prime plus D prime quantity times A prime plus C prime. Now you say, well, yeah, that looks like it's in POS form. It is in POS form, but you took the inverse of the SOP. So this equals the inverse of the POS expression. It's not the POS expression, it's the opposite of the POS expression. So the correct answer would be F prime equals this, not F, because you inverted it. So yes, when you do the inversion of the SOP expression, it looks like you've got a POS expression now, but you don't. You have it in POS form, but it's not equal to F, it's equal to F prime. If you wanted to get it back to F, you'd have to invert it again. And if you invert it again, take away the prime, you're back to what you started with. You're back to this, which was your SOP expression. If you really want to convert it, you have to do what we did in use switching algebra to do the conversion. And in this case, you can, it's a little bit of a hassle, actually. So it's not quite that simple. It's easier to use the K-map. The way you do so we could take switching algebra, and I don't want to go through that because it takes time for no particular purpose here. But I'd factor out the C, and then I get, or actually, I probably just let this be X. No, let's see, that's not really a good way. Oh yeah, I'd probably let this be X. Or no, I let these two would be X, and that would be YZ here. So then that would give me B prime D prime plus CD plus A quantity times B prime D prime plus CD plus C. And then I can drop that term because of the C and the C. Can't do anything with this. So so then what I would do, then I would take this as X and this is YZ. And I keep doing that until I finally got it into some SOP form. And it's obviously going to be a pain in the butt to do this. So it's complicated. You can't just take the inverse. You have to go through this whole process. Or you can use a K-map. And instead of doing the ones, we'll do the zeros. And I have done that here. So now I have the zeros. And now I just pretend those zeros are, I pretend these zeros are ones. I write down what the term would be and I invert the term. That's how I do it. It's a trick. But it does not mean that the SOP is the inverse of the POS. I never said that. It is not true. Don't think that. Okay. So, so this group of four would be B, C prime. This row would be C prime D. Oh, so, well, sorry, C prime D. And this wraparound group of two would be A prime B D prime, A prime B D prime. Oh, sorry, A prime B D prime. But I have to invert these to get the POS terms. So I invert BC because these aren't ones, they're zeros. So the correct term for that would be B prime plus C. That's that one. The correct one for this would be C plus D prime. And the correct one for this would be A plus B prime plus D. So my POS solution is B prime quantity, B prime plus C times C plus D prime quantity times A plus B prime plus D. Okay, so it's 1, 2, 3 terms, two variable terms, 1 3 variable term. Now, if we use switching algebra, we could eventually get it from this form into this form, or this form into this form. But here's the important take-home point. B prime, D prime, plus CD plus AC equals exactly, for every value of ABC, B prime plus C, C plus D prime, and A plus B prime plus D. Okay. So this expression exactly equals that expression. And you can manipulate one or the other into the other form using switching algebra, or you can plot it on a truth table, plot the zeros, then take the ones and write the one expression, and you'll get the opposite answer. But just to convince you that that is true, let me pick a value. Let's look at it for A equals 1, B equals 1, C equals 0, and D equals 0. Now, what value should it be when we plug this in? Well, let's look. So that's 1, 1, 0, 0. That's C. So if we go here, 1, 1, 0, 0, the output should be 0. Okay, the result should be 0 on both sides. Let's see if it is. So we put in D equals 0. So D prime is 1, B equals 1, B prime is 0. So this term is 0, plus CD, C is 0. So this term is 0, and D is 0 too. And then AC, C is 0, plus 0. So this side equals 0. What about this one? Well, we have B prime plus C. Well, B prime is 0, or C is 0. So that term is 0 multiplied by that, by all of this. This is going to be 0. I don't even have to do the other terms. So I can see that both sides are 0, which is correct. They're equal to each other, and that was the desired value for 1, 1, 0, 0, supposed to equal 0. So it does work correctly. And for every one of the ABCD values, this side would evaluate to 1 if that's what F was, or 0 if that's what F was for that row. And so would the other side. They're exactly equal. They are not the inverse. Don't ever think for a minute that the SOP form is the inverse of the SOP form. It's not. Now, if you invert either one of them, if you just invert the expression, you will convert. Anytime you invert a SOP expression, you immediately turn it into a POS expression. But it's not the answer for the truth table, because it's the opposite of the correct answer. It's F prime. Okay. And you don't want to mess with F prime. You never want to forget F prime. You don't want to do F prime. You want F. All right. I hope I make that clear, because I see this all the time, and it drives me crazy because it's wrong. And I never teach it. I never say it. And yet a lot of students think this for some reason, and I don't know why, but it drives me crazy. All right.
Dr. Martin,
Yeah.
can you really quickly go over how you determined that there were 4 exactly prime implicants?
Sure. So if you look at the picture, so we have one group of 4 with the corners. And again, normally when I use the term prime implicant, I'm not talking about the zeros. I'm only talking about the ones. I don't do it with the max terms. I only consider it with the min terms. Now, I suppose you can do implicants with max terms too, but I mean, we certainly can write down a POS solution using the zeros. But normally when I think prime implicants, I'm really talking about the ones, okay? And in this case, we have the 4 corners, right? You can loop all those by wraparound together. We have this row, and we have this group of 4. And then this is hard to see, but there is this wraparound group of 2 that's a consensus term. And that's because it's a group of 4 that can't be combined with any other group of 4 to make a group of 8. And it is a legitimate group of 4, but all 4 of the ones covered by that group of 4 are also covered by other prime implicants. So it's a non-essential, and that pretty much makes it a consensus term. All non-essentials are essentially consensus terms.
So do we need to show that additional group of 4, the consensus one, or is it okay if we don't show it?
Well, if you don't show it, then you won't count 4 prime implicants, you'll only count 3. So you'll be 1 off. It is a prime implicant, just not necessary.
Okay, so we have to show it, right? Since it says loop all the prime implicants?
Yeah.
Okay.
Yeah, if it said loop all the essential prime implicants, then you could leave it out. But it doesn't say that. So give a good hard look at these maps and make sure you don't miss one. Now, I'll be the first to say this was a tricky one. The one on the test probably won't be that tricky. This was tricky. And the 4 corners is kind of a little tricky too. There are a number of them that can be tricky to see. So what you should do is make some maps and kind of look at them and see if you can, see if you can see them all. We'll do another one in a minute, but yeah, I mean, that's a good question. Okay, next problem. And then the other thing is, which one of these expressions is simpler? The POS expression or the SOP expression?
SOP.
That's right. The SOP is simpler because it has 3 2-term variables, and the POS has 2 2-term variables and 1 3-term variable. So it has 1 more input into one of the gates. So they're very close. It's not like a big difference, but it is slightly, the SOP is slightly simpler. Does everybody see that?
Yes, sir.
Okay. All right, next. So I'm gonna fold this up. All right, so here we have a problem. We want to generate F with a mux. And what is F? F is equal to the min terms 0, 1, 2, 5, 7, 11, 13, and 15. All right, so the first thing we do for the mux problem, we do have to use the truth table. It's not so critical for the demultiplexer, the demultiplexer, and but it is, you pretty much have to do it for the ROM, and you certainly have to do it here for the 8-to-1 mux. So let's copy it over. Okay, so here's our 4-variable truth table, 16 rows, 2 to the n, n's 4, 16 rows, and we put in a 1 for 0, a 1 for 1, a 1 for 2, skip 3, 4, a 1 for 5, skip 6, a 1 for 7, and you can always check. So 0, 1, 1, 1. Okay, that is 7. That's right. And then I know A is 10, 10, 1, 0, 1, 0. So I know B, which is 11, is here. And then 12, 13, 14, 15. Now I put in all the min terms. I did not write the zeros. If you want to write the zeros, go ahead, knock yourself out. I like to leave them blank because it just makes it cleaner and less confusing. And if you make a lousy 0, you can sometimes mistake it for a 1. So I just don't write anything when it's a 0. And then when I'm writing the zeros in, like I did here in this little K-map, I didn't put the 1s in. But if you have don't cares, you always include all the don't cares all the time in both the POS. If you're looking for a POS solution with the max terms, or if you're looking for an SOP with the min terms, always include the don't cares because you might want to use them, you might not, but you should at least look at them and consider that whether you want to use them. Okay, now that we've done this, I like to divide the truth table up into pairs of rows like this. And you want to start with 0, 0 and 1 in a pair, 1 and 2 in a pair, 3 and 4, 4 and 5, and so forth. And make sure you come out with the last 2 rows also a pair. And if you don't, then you dinged up. All right, now I look at F. And all I have to do is look at F. Anywhere I see 2 1s, I know I put in the constant 1. Turns out the only pair of rows with 2 1s is the first 2 rows. Then I look for where I have 2 zeros. And I happen to have 2 zeros here, so I put a 0 there. That's the only place for that. Everywhere else, I have a single 1. All right, where you have a single 1, the single 1 is either exactly the same as D, or it's the opposite of D. In his case, F is 1 when D is 0, F is 0 when D is 1. So I put in the opposite of D, which is D prime. Here, F is 0 when D is 0, F is 1 when D is 1. So I just put in the regular old D. Here, it's the same, so I put in D. Here, it's the same, I put in D. Here, it's the same, I put in D. And here, it's the same, I put in D. So I have D here, here, here. I have a 0 here. I'll put a bar in it to make sure I don't confuse it with my D's. I have a D here, a D here, a D prime here, and a 1 here. So 1 goes into I0, and all that means is I just tie this up to VCC, or VDD, whichever you want to write. And here, I just tie this down to ground. And all the rest of it, I'm either going to put in D or D prime. Now, usually you have a flip-flop where D is coming out of it, so you can pick the Q or the Q prime to get D or D prime. And that is a real help. That's why flip-flops usually provide both the prime and the non-prime output. Now, the only other thing I have to do is I have to make sure that my ABC, which the reason I divided it up into pairs of rows, my ABC are always the same for each pair of rows. For the first 2, it's 0, 0, 0. For the next, it's 0, 0, 1. For the next, it's 0, 1, 0. For the next, it's 0, 1, 1, and so forth. For the 2 rows in the pair, A, B, and C are the same. I now have to put A, B, C into here, A, B, C, and I have to put A as the higher order. That would be A2. C is the lower order. That would be A0. Sometimes these are cell 0, cell 1, cell 2, cell 0, cell 1, cell 2, cell 1, cell 0, whatever. But you should be able to look at this and figure what's the higher order variable. In this case, it's A2 rather. And so I put A, my higher order variable, into A2. I put B, my next, and I put my low order variable C. Well, D is, I guess, really my low order, but of the ABC, C is the lowest. I put that into A0. And then D gets accounted for by being used as one of the inputs. So remember, I only have 4 choices for these inputs: 1, 0, D, or D prime. That covers all 4 possible ways F could be lined up for that pair of rows. It could be 0, 0, it could be 1, 1, it could be 1, 0, and it could be 0, 1. And this covers all 4 possibilities. That's how you implement a function with a multiplexer. All right, any question with that? All right, let's say instead of a multiplexer, we
No, sir.
have, go ahead, question?
Oh, I was just gonna say no, sir. I don't have any questions.
Great, okay, good, wonderful, perfect. All right, let's say we're gonna do it with a decoder. All right, so here's my decoder. And my function is 0, 2, 4, 5, 7. I'm not even gonna put it in here. What I know I have to do with a decoder, crap, you can't see it, hang on. What you have to do with the decoder is you have to add an additional OR gate to make it implement a function for you. So in this case, I'm going to add an OR gate here to my output F. Okay, we'll connect that like that. And now all I have to do, well, then I have to connect my 3 independent variables to my 3 select lines. A, B, C. They may not be labeled A, B, C. They might be labeled A, B, C lowercase, or they might be, I don't know. They might be A2, A1, A0. They could be something. But A has to be the higher order. C has to be the lower order. They're not even necessarily lined up in the right order on the schematic. They might be. They probably are. I have to ground my chip select to turn the chip on. Otherwise, they'll all be tri-stated. So all I have to do then is I have to look at output 0, output 2, 4, 5, and 7. So output 0, I connect it. Output 2, 4, 5, and 7. Now, obviously, I need a 1, 2, 3, 4. I need a 5 input OR gate. If I didn't have a 5 input OR gate, I could use 2 3 input OR gates and then put that into one output OR gate using the fan, using limited fan in problems.
Is it always gonna be an OR gate?
Yeah, because you're ORing them together. So remember, when you do an SOP solution, you're writing A, B, C plus A, D plus whatever. So these are ORs. So you're doing an SOP solution. This chip's generating all 8 possible AND terms. And then you're connecting the ones you need, which happen to be your min terms, to the output OR gate.
So it's the POS?
No,
Oh, okay. Okay, you can forget that question. Sorry.
thank you. Because it was starting to send me into a depression. Yeah, remember, SOP is input AND gates, 1 output OR gate. POS is input OR gates, 1 output AND gate. Right? Okay, let me give a little quiz since we're on this. If I give you a network that looks like this, and we don't even know, these are some, A, B, C, A, D, C, D. What form is this in? Is that an SOP or POS?
It's POS,
Ah!
SOP.
All right. What are your input gates?
They're AND gates.
Right. And what is your output gate?
It's a OR gate.
That is always SOP.
Okay.
Now remember, I told you that SOP is designed to confuse students, right? So the S is the output, but they put it first just to confuse you. And the P is the inputs, and they put it last just to confuse you. So don't let their dirty tricks work, all right? I don't know who came up with this. It's a terrible idea. So remember, sum means OR. Product means AND. So really what we should say is this is an OR of AND terms. But really what we should say we put in AND terms and we OR together. And then you would have the AND first and the OR, and it would look like this. But they wrote it backwards. They call it sum of products. Okay, so these are the products, and this is summing them up. Because sum means ORing, and products mean ANDing. Remember, there is no such thing as multiplication, division, addition, or subtraction in switching algebra. We just stole the words and we apply them inappropriately to the concepts of ANDing and ORing. All right.
Got it.
So, yeah, you've got to be straight on this. Do not let this be confusing to you. Okay. So you just have to look at it so it makes sense. Okay. Okay. So we did the multiplexer. We've done the decoder. What's left? The ROM. All right. We're going to do the ROM next. So we want it. You're going to have one of those 3 problems. And we don't know which one. Well, I do, but I'm not going to tell you. All right, so you need to know how to do all 3 of them. Now the ROM is a little different. The ROMs, of course, take a lot more hardware to put them together because you're fully decoding all these addresses all the time. There's no now you're not there's no, well, you're not really with all these, there's really no simplification going on at all, right? When you implement it with the MUX, you don't simplify anything. When you implement it with the decoder, you don't simplify anything. You're just taking them in terms. And that's the same thing with the ROM. There's no simplification here at all. You're just transcribing it from the truth table into the ROM. And same with the MUX, same with the decoder. Yeah, but when you implement it with gates, now you want to minimize the term so you don't have to use as many gates. But when you use these things, which is what's in FPGAs, there's no point in simplifying it most of the time. Sometimes there's still some use in it, but most of the time not. All right, so the way we do this, we got 1, 2, 3. We actually have 4 functions here we're going to implement. So here's our truth table, 4 independent variables, 16 rows, 4 output columns. And I'm just going to do them in order, F1, F2, F3, F4, like they're labeled here. So we have 1, 2, 3, skip 4, 5, and then we have 15 and 13. All right, the next one, we have 0, 2, 4, 6. Crap. 0, 2, 4, 6. And then we have 9 and 11. All right, I'm going to find 9 here. 9's right here. 9 and 11 is B. It's here. And then the next one is 2, 5, 9, 2, 5, 9, 13, 14, 15. So 2, so 0, 1, 2, 3, 4, 5, and then 9. I know 9's right here. 2, 5, 9, 13, 14, 15. So 15, 14, 13. And then this is 15, 13, and 6 and 7. So I know 6 is right here, and 7 is right here. So 6, 7, 13, 15. And that's this one right there. Now, I could also write the zeros in, but I'm just leaving them out for clarity. But obviously, if you're going to fill the ROM up, actually, the truth of the matter is most ROMs start off all 1s, and you flip the 1s to zeros. When you erase a ROM, you erase everything to a 1, and then you have to write the zeros in. But we'll pretend we don't really know that, and so we're just going to write the 1s in. So we just take exactly the copy of this, and we map it straight into here. I'm not going to do that. And then the other thing we need to do, what about the outputs? The outputs here are labeled output 0, output 1, output 2, output 3. Well, if we put this column in here, then that would be F1 coming out here, F2 coming out here, F3, and finally F4. And then what about our address lines? We've got 4 address lines because we have 16 rows, 2 to the 4th, 16. So we have to put these exactly in hierarchical order, A to the high order, and D to the low order, and B and C in between in order. And this hooks up our ROM. All right, clear as mud? Yes?
Yes, sir.
All right, so it's really easy, right? All these are really easy. ROM, decoder, multiplexer. The only one you have to kind of think about is the multiplexer. You got to divide it up to rows of 2s, figure out whether to put in a 1 for that row, a 0 for that row, a D for that row, or a D prime. If you're using an 8 to 1, if you're using a 4 to 1, you do the same thing only with C and C prime. Because you only have 8 rows, you have A, B, C, and then A, B go in here. You don't have 3 select lines, you've only got 2 for a 4 to 1. But for an 8 to 1, you do have 3, and then you have to have D. Okay, and that generates your output F. The only tricky thing, remember to ground this chip select if you're doing a decoder. In this case, get your ABC right. In this case, get your ABC right. In this case, get your ABCD right. Always got to have your independent variables are controlling your select lines or your address lines, whichever you want to call it. Okay. All right. Let's so we'll go through, we'll finish the second page. We'll do a couple of these. So
Hey, Professor,
yes.
I was wondering if we could go over the timing diagrams and
Yeah, I'm going to do that.
the
Yeah, I'll do
flip-flops.
I'll do
go
the
ahead.
timing diagram next, and then I'll just talk briefly about these other things. I'll just go through them once.
Thank you.
Maybe I'll just go through these others real quick, and then I'll do the timing. All right. So here's a flip flop. So what kind of flip flop is this?
Falling edge.
Yeah. Okay. It is a falling edge clock, but that doesn't tell me what kind of flip flop.
The JK.
Is it-
JK.
Okay. So what about that?
Oh, T.
Yeah.
Sorry about that. Yeah.
yeah, you got stampeded. Don't jump to conclusions. Look at the whole thing. I'm not trying to fool anybody, right? So what kind of flip-flop would this be?
It's a
D.
flip flop, yeah.
That's a D, right? What's this?
Okay.
It's a JK.
That's a JK. Pretty easy, right? I mean, it's not like I'm not giving it to you. All right. Notice this has a set. What does this one have?
Clear?
Clear.
That's right. What does this one have?
Clear.
Yeah, it's got an N at the end, so we would normally call it a clear knot. And that's because it's got this bubble up here, which could be colored in, might not be. It can be open or colored. And that means it's an active, what? High or low clear?
Low.
Yes, active low. What kind of clear do we have here?
Active high.
That's right. Here we have a falling edge clock. What kind of clock do we have here?
Falling edge.
Yeah, I guess we're falling edge. All right.
Oh, yes.
What kind of an asynchronous input do you see there?
It's a active high, right?
It is active high, but what kind of, so that's a clear. What's that?
It's a set.
Yes. So the clear sets the flip-flop to 0 or clears it to 0, and the set sets it to 1. So when you say set, you mean put it to 1. When you mean say clear, you mean put it to 0. So the set sets it to 1. The clear clears it to 0.
Professor, what does clear N do?
The clear N stands for clear knot. It's just like clear with a tick mark or a bar over it. Sometimes we'll write clear with an N at the end for clear knot. It just means it's active low. So you would, if it says clear knot like this one does, you would expect a bubble. So that would tell you that the asynchronous input is asserted when the input is low.
It's only true when the input is 0, just like the variables. They're only true if they're not, if the input is 0.
Right. Yeah. You just, however you want to kind of discipline yourself to think about that is fine. Just remember that it's when you've got the bubble, it's active low. So when it's active low, it's asserted when it's low, it's deasserted when it's high. But in this case, it's asserted when it's high and deasserted when it's low. And that's because there's no bubble. Now, if you had somebody put a clear knot on this, but didn't put the bubble, then that's just a horrible mistake. And you don't really know, then you'd have to test the thing to see how it really worked, because some terrible engineer wrote the data sheet and made errors on it, which every data sheet I've ever looked at in enough detail, I usually find an error or two. Every one. It's amazing. They're just not error free. And that's because they're written by people like you and me. And we're engineers, we're not, literary experts. And we normally, we make mistakes. But then, they're complicated documents, and, most of them, like on microprocessors, they're usually 500 or more, 600 pages. It's easy to make a mistake. Okay. All right. So we want to know what kind of flip-flop, what kind of clock, does it have a clear knot or a clear or a set or an asynchronous input? Yes or no? In this case, yes. It does it have a clear knot? No, it doesn't have a clear knot. So that would be a no. It's got a set. Is the asynchronous input active high or active low? You guys tell me. Which is this one? Active high or active low?
Active high?
Yes, it's active high. Okay, so here we have this fan in problems. So let's say we only have gates with 2 inputs. Here we have a 4-input OR gate. Here we have a 4-input NOR gate. Remember, with the NOR gates, you've got to put inverters between the layers. So with an OR gate, you don't have to. So with an OR gate, your 2 input, you can make a 4 with 2 2s. So there's a 2, there's a 2, and then you just put a 2 here, and they go in there. And now these are equal. This 4 input is the same as these 3 two input NORs, A, B, C, D, if you had A, B, C, D, you just put A, B in here and C, D there, and now you've got the same thing. Obviously though, you have, if this is 10 nanoseconds and these are 10 nanoseconds, now the effective propagation delay for this is 20 nanoseconds. So you have increased delay, or you've increased your propagation delay, but or your inertial delay, as we call it in very long. But other than that, it's fine. However, you can't do that when you have this bubble on there. It screws everything up. Now you do the exact same thing, but you have to put. So here's your NOR, two input NOR, bubble on the output, and then you have to put an inverter in here, and then you can put it into your output NOR. Same here. Two inputs here, bubble on the output, have to have an inverter in here. And now these are now the same. But if you don't put that inverter in with NORs, it screws it up. You get the wrong answer. And some of you probably ran into this on your design problems. Hopefully. Yeah. All right. This is consensus terms. Really no big deal. Two essential prime implicants, one non-essential, which is the consensus term. If you're sitting here in this square right here, or in this square, and you change one of the variables, so you would move down to this square, then you'd go like from, I don't know, I have to write it out. But anyway, you could have a hazard if there's delay problems because of different delays with gates, and you could fix it with the consensus term. And the reason you can fix it with a consensus term is, well, let's look at them. So this one would be B, C prime, D prime, and this one is A prime, B, D. So if you notice, the D changes from D here to D prime there. So we have a D here and a D prime there. If the D changes, let's say B equals 1, C prime equals 1, which means C equals 0, and A equals 1, A prime rather, A equals 0, A prime equals 1, and again B still equals 1. So this term would be, if D prime is 1, then this term would be 1, and you'd be up here in this term right here. If the D changed to 0, then you just plop down into this term, and the D would have to switch from 1 to 0, or from 0 to 1. And because it has to go through an inverter, potentially, there might be a hazard. So the way you fix that is you add in this consensus term, takes away the hazard. Well, what is the consensus term? The consensus term has A prime, B, C prime. Notice the D is not even present in that term. And remember, we said B is 1, and A prime is 1, or A is 0, however you want to write it, and C prime is 1, or C is 0, however you want to write it. So this term stays at 1 because the only thing that changed was the D, and the D is not even in this term, so it fixes the hazard. Okay? Does that make sense?
Yes, sir.
All right.
Yes.
You should be able to draw out this VHDL circuit and answer questions about it. So this is in VHDL. So E equals A and B and C. So you write a little AND gate, A, B, C, and the output is E. And then you have a little OR gate here, A and Y. And the output of that is F. And then you have a little AND gate here with E and F going in and H coming out. And then there may be some questions. So just remember, AND gates, just remember, you should know absolutely cold how AND gates and OR gates work, right? You should know right off the top of your head that if we look at a 3-input ABC, so 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and 0, 1, 0, 1, 0, 1, 0, 1. Okay, now, so that's our ABC. And then we have AND gate, we'll call it AND, and an OR gate, we'll call it this. Okay, the AND gate is going to be 0, 0, 0, 0, 0, 0, 0, 1. And the OR gate's going to be 0, 1, 1, 1, 1, 1, 1, 1. Now, they're not actually the numerical inverse of each other, but they are the functional inverse of each other. So we take an inverse of an AND gate, we turn it into an OR gate, which is kind of interesting since they really aren't, 0 is not the opposite of 0, 1's not the opposite of 1. So they have the same output for 1, 1, 1, and they have the same output for 0, 0, 0. So they're not really the inverse of each other, but we think of them as the inverse functionally. And that's one of the great mysteries to me. But anyway, that's how it is. So you just have to accept it. But why an AND is the inverse of an OR still sort of seems weird to me, because it's not true. It's not true numerically, but it is true logically. So enough said. I don't want to confuse you before the test. Okay, so does everybody know this code?
Yes, sir.
All right. If you don't, take some time to think about it, but you have to know this code. Now, what about an XOR? Okay, I'm sorry. Yeah, exclusive OR. What about an XOR? Okay, the XOR is, it's 0 there, 1, 1. It's 0 here when you have two inputs are 1, back to 1, 0 and 0. What is it for 3 1s?
0.
No, it's 1.
Really?
Make sure you know that. This is also not really a true statement, because exclusive OR would mean that this should be 0. So it's really more like an odd gate. But there is such a thing as an odd even gate, odd and even gates, and they behave a little differently. So I find myself scratching my head all the time. But anyway, we call this an XOR gate. That's what it is. It's not an odd gate, but it really functions like an odd gate in my view. Okay, let's do the timing diagrams and then we're going to quit. Oh well, this one is simple. You just have to plot these terms, and then extract the, in this case, extract the min terms. In this case, extract the max terms. In this case, extract the max terms. So you might have to extract the max terms and the min terms. I don't know which. All right, AC. Okay, so remember our alternate labels. Sorry. Well, this is B, and these two are A, and these two are C, and the middle two are D. Usually we write the B down here. I don't know why I put it up there. All right, so AC. So A means it's these two columns. C means it's these two rows. So that gives us this four boxes. B, C, D prime. B, D, C prime. So B is the middle two columns. D is the middle two rows. So that's these 4 here. And then C prime would be the 2 up here. And then A prime, B prime, C prime. A prime are these two columns. B prime, A prime, B prime would be this row. And C prime would be these first 2 up here. So those are our ones. And that would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would be up here. And then 13 through 15. Okay. You should write 14 in. I shouldn't have done that. 13, 14, 15. Okay. That's really easy. And if you did the zeros, then you just think about the zeros and you do them. If you had to do the max terms, it would be 2, 3, 4, 6, 7, 8, 9, 12. Okay. All right. Let's do these problems. All right. So we'll do these. All right, so here we go. Now, if you follow the rules I'm going to give you, you will always get this problem right unless you make a stupid mistake. If you don't follow these rules, then you're kind of on your own because you'll probably make a mistake. But if you follow these rules, you're very unlikely to screw it up. Okay, so pay attention. And okay. All right, I think so. All right, let me just check one thing. Yeah. Okay. Oh, I wanted to say, Amy, did you get credit for the help session or for the corrections?
I saw something that said, but it didn't update my score.
Yeah, no, the score wouldn't change. There should be a column next to the score where you have the new score, but it's not in the original column. It's just next to it. Check and see. If you didn't get that, send me an email. I hope I got it straight, but I don't know. I was a little confused. I'm sorry. All right, but check it in. If there's a problem, let me know.
Is it correction 1?
Yes.
Then yeah, I got.
Okay,
credit for
good.
that.
Okay, good. Okay, good. All right. Moving on. Okay. So first thing is read the problem. Do not start without reading the problem. Because who knows? Q might not start at 0. And if you assume that and don't read the problem, you may mess up. Using the D flip-flop picture. Oh, look, I told you it was a D flip-flop, so you don't even have to think about it. And you always know the D flip-flop's easy. Whatever D is, when the next clock hits, that's what it's going to change to. D is 0, it's going to be 0. If D is 1, it's going to be 1. Doesn't matter what it is now. It's either going to go, whatever D is, that's what it's going to become. All right. Write in the tracing for Q in the timing diagram. Assume the delay for outputs to change after the active edge of the clock R set is 10 nanoseconds. Okay, what that's telling us is that whether we're changing the flip-flop with the D input in the clock edge, or whether we're changing it because we're asserting the asynchronous input, in this case, it's a clear, and it's active high. So when we take the clear high, we assert it. When it's asserted, there'll still be a 10 nanosecond delay from the moment we assert it to the moment the output actually does go clear. Okay, so you always have to factor that in. We'll do that in a second. Assume setup and hold times can be ignored and that Q equals 0, T equals 0. So I'm going to go ahead and mark Q equals 0, T equals 0. Okay, the first thing I'm going to do is I'm going to look at my asynchronous input. So what is my asynchronous input in this case? Somebody tell me.
It's active high, right?
Yeah, it's active high. And what is it? A set or a clear?
It's a
Clear.
clear.
Okay, clear. So it's going to be active. It's going to be asserted when it's high.
asserted.
So is it going to be asserted in this area or in this area?
This area.
Second.
Yeah, you're right. This area. All right. It's going to be asserted when it's high. Now, if it were active low, I would color in the part over here, but it's active high. So I'm coloring this in. If it were active low, it would have a bubble, but it doesn't. So it's active high. Okay. Same here. Now, what is the active edge of the clock? Is it a rising edge clock or a falling edge clock?
Falling.
Edge.
Okay, so I'm gonna mark all the falling edges. Okay, the first falling edge I see is right here, and that's fine. I'm gonna highlight it. Now, what about this edge? Is this active edge gonna do anything?
No.
It's gonna be blocked by my asserted clear. So I'm just gonna X it out. This is also gonna be blocked by my asserted clear, and so is this one. So I don't even have to worry about those. Now I mark this one, mark this one, mark this one. Now I know that on this active edge, that's when I'm going to read D. So now I'm going to go come down here and I'm going to write in the value for D. What is D at this active edge?
1.
Right.
That is right. It is 1. Or true or high. All true. What is D at this active edge right here?
0.
0. What is D at this active edge here?
1,
And what is it out here?
0.
Correct. All right. Notice 1, 0, 1, 0. Now I'm not going to screw it up and misread it because I've already thought through and written it in. Now, the last thing I want to do is I want to write in all the points of possible transition of my output Q. Now, Q can only transition 10 nanoseconds after an asserted asynchronous input, in this case, a clear, or 10 nanoseconds after an active edge of the clock. But of course, these edges are blocked. So I only have to worry about this edge, this assertion right here, which I'll highlight, the assertion right here, which I'll highlight, this active edge, and this. So I have to worry about 1, 2, 3, 4, 5, 6 possible transition moments. Now, it doesn't mean it will transition. It just means it can only transmission at those points, right? It can't transmit, it can't transition from low to high or high to low anywhere else, only at those points. It may not transition at those points, but it can't transition anywhere else. So let's mark those points. And then those are the only points we have to think about in the entire graph. And everywhere else, we can just continue a line until we get to the next transition point. I should say possible transition point. So so here's where my edge is, 10 nanoseconds later, my first possible transition point. Here's my asynchronous input asserted, 10 nanoseconds later, my next possible transmission point. The next one's all the way out here, 10 nanoseconds after this edge, is right here at 160, possible transition point. Next edge asserted here, 10 nanoseconds later, at 180. Here asserted at 230 and possible transition at 240, 10 nanoseconds later. Here it's asserted at 250, possible transition, 270, possible transition at 280. So these 1, 2, 3, 4, 5, 6 X's are the only points where the output can change ever. Might not change there, but it cannot change anywhere else. So if you have it going up and down some other place, you're wrong. You know that instantly because it's not at one of these X's. So that's going to keep you from making a stupid mistake. All right. At this one, our D is 1. It's being driven by this falling clock. What happens at this transition point?
Goes up.
Yes, it goes from low to high. Now I know it can't change to here, so I'll draw that line to there. Now at this point, what happens? This is a clear. So what's going to happen at this transition point?
High to low.
High to low. Going to stay low all the way out to here. Can't change anywhere in here. What's going to happen at this possible transition point? The active edge is here. D is 0. What's going to happen?
It's gonna go from low to high.
Wrong.
0.
That's right. It's going to stay at 0 because D was 0.
Okay.
So it's just think of it this way. It's the exact same thing. So I don't know if you knew this or not, but my uncle's cousin's college roommate was your sister's uncle's boyfriend. So what does that make us? And the answer is absolutely nothing. That's out of Spaceballs, by the way. Except I don't have it right. I don't know what it was exactly. It involved a college roommate though somewhere. Okay, so yeah, so this is just nothing, and nothing's going to change it. It's going to go just straight on because this D was 0, so it's not going to go high. It's going to stay 0. All right, now we have in the next possible transition. What's this? That's a clear, right? Got asserted. 10 nanoseconds before, now we're 10 nanoseconds later. What's going to happen? Remember the college roommate.
Stay at the bottom.
That's right. Nothing's going to happen. All right. Go out to here. Now we have another falling edge and D was 1. What's going to happen? That was, of course, 10 nanoseconds earlier. Now here we are at the possible transition point. What's going to happen?
Rise.
Yep,
Right.
it's going to go up to 1. It's going to stay till here. Here it's a 0, so it's going to fall, and it goes on out at low. So we only have 4 transitions. These 2 we didn't transition at all. All right, clear as mud.
Yes.
Sir.
All right, we'll do one of these others that's got a little different. All right, let's do one without an asynchronous input. So no asynchronous input here. All right, so same thing. Read it using the JK flip-flop pictures, write it in tracing for Q in the timing diagram. Assume the time for the output to change after the active edge of the clock is 10 nanoseconds. Assume setup and hold times can be ignored and that Q equals 1. Oh, oops. Q equals 1 at 2 equals 0. All right, we better mark that. Okay, now in this case, do we have an asynchronous input?
No.
We do not, right? None. So therefore, it only depends on J and K and the clock. So do we have a rising edge or falling edge clock?
Rising edge.
Okay, so the first thing we can do in this one is mark all the rising edges because there's nothing to block them. And then we're going to go back and we're going to mark our J and K at every active edge. So with this active edge, what is J?
1,
0,
0 is correct. 1 is incorrect. 1. K is 1. Okay, this active edge, what's J
1,
and what's K?
1,
Correct. At this active edge, what's J?
1,
1,
What's K?
1.
Yeah, just barely, but it is. And since we don't worry about setup and hold times, we're not going to worry that it's pretty close. It might not have enough hold time possibly, but we're not going to worry about it because it said assume setup and hold times can be ignored. So we're ignoring them. All right. Here at this active edge, what's J?
1,
K?
0,
0.
And here, J is
0,
and K.
1,
Yep. And here, J
1,
is that's 1, it's barely, and here's K.
0.
Okay, now, how does the JK flip-flop work? You do have to know this.
No, wait. We
So you should remember that J sets, K clears. If they're both 0, it holds. If they're both 1, it toggles. So that's really easy, right? If you have JK, you have 0, 0, 0, 1, 1, 0, and 1, 1. So this is toggle. This is hold. This is clear. And this is set. The middle two make up a D flip-flop and the outer two make up the T flip-flop. Because a T flip-flop either holds or toggles, and a D flip-flop always follows D. And remember, to make it a D flip-flop, we would put an inverter into K. So, and then we just connect it to J. So if D is 1, J is 1 and K is 0. If D is 0, J is 0, K is 1. So it's always going to force that change. Does that make sense? No toggling, no holding. Unless D, of course, is the same as it previously was or different. But it just follows D. It doesn't ever really hold irrespective of D. It doesn't ever toggle irrespective of D. It always follows D. Okay. So now let's go through and list all our possible transition points. All of them are going to be, in this case, every single one's going to be 10 nanoseconds after the active edge because there's no asynchronous input. So here's the active edge, possible, active edge, possible, active edge here, possible transition, active edge here, possible, active edge here, possible, and active edge here, possible transition. All right, so we know we can go to here before anything's going to happen. What's going to happen at this point?
Rise.
It's gonna go down to 0, right? Because J is 0 and K is 1, or it was at least at that point. Okay, now it's going to stay down here for sure till there. They're both 1. So what's going to happen at this point? 10 nanoseconds after the clock edge.
It's going to rise.
It's going to toggle. Toggles up,
Uh,
goes to here. What's going to happen at this point? Well, we still have 1, 1, so it'll toggle again. So down it goes, stays down for sure till here. Now it's J set, K is clear. So J is 1, K is 0. So it's going to be like a D. It's just going to go up, right? It's going to go all the way down to here. Now what's it going to do here?
It's going to fall.
That because J is 0 and K is 1.
It's
Stays
clear.
down to here. Now what's it going to do there?
It's going to go. It's going to rise.
Yep, back up because J is 1 and K is 0. And it stays there until whenever. All right. So now we have transitions at 30, 80, 120, 170, 210, 260. We have high to low transitions at 30, 120, and 210. We have low to high transitions at 80, 170, and 260. Okay. And I'm probably going to ask you about high to low transitions. So you have to pay attention. You don't want to, if I ask you for high to lows, don't give me low to highs and vice versa, right?
Professor,
Yep.
to change the JK flip-flop to a D flip-flop, it's
Just like I showed you here.
it's that inverter, and what's that circle behind it? The one.
That's the D input.
Oh, okay, gotcha.
And then the inverter has a bubble on it, of course.
Dr. Morton,
Yeah.
in the previous problem we did, could you just put it back real quick? I had a question. Okay, so if the asynchronous clock in this, instead of clear, if it was a set, then every time we hit the block, we would fall. I mean, we would rise instead of fall, right?
Yeah, so if this were a set, then what you'd have here is this would just continue out to there. And you wouldn't have that. And then this would go back up here and continue all the way to there. So it'd only go down for that little bit.
Thank you.
All right, we'll do one more, only this one I'll change up a little bit, and we'll make the asynchronous input active low. I'll put a bubble on it, even though it didn't really have one, but it might on the test, you never know. All right, so here's our little bubble. Now it's going to be an active low set. We'll do same thing, read the problem, D flip-flop, write the tracing for Q and the time diagram, assume the delay for the outputs to change after the active edge is 10 nanoseconds, assume setup and hold times can be ignored, and that Q equals 0. Okay, so Q starts at 0, that's good. All right, so the set is active low. Okay, so that means the set's going to be asserted here and all this way out here. All right, and then we have a rising edge clock. So the clock's going to be blocked here, active here, blocked, 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 blocked. We're going to assert it right here. So the first assertion occurs right here. And so it could impact us as early as 10 nanoseconds after the beginning of the time. And then the next possible transition is 10 nanoseconds after this active edge, which is right here. The next one is 10 nanoseconds after this one, which is here. The next one's 10 nanoseconds after this one, which is there. And then the next one are all blocked, so there's no more. So we only have 4 possible transitions. We start at 0, we get here. It is a set, it is asserted. So it's going to go up, it's going to stay up, gets here. Oh, I didn't put the D. The D is 1 here, and that's the only one we have to consider. Oh, no, sorry, the D is 0 here. So we have to consider those 2. So it's 1 here, so it's going to stay up. And then here it's going to go down. Here it's going to go back up from the set, stay up all the rest of the way. So that's what it's going to look like. So we have 1 high to low transition, another high to low. So 1 at 10, 1 at 110, and then only 1 low to high, 2 low to highs, 1 high to low at 100. Okay,
But
yeah,
the active rise is X'd out, but it rises at 10 because of the
asynchronous input,
okay.
because we have to assume the set was asserted at time 0 because it didn't tell us differently.
Okay.
Probably would specify that if, yeah, it's a little bit bad, but you have to assume that.
And why do we have to take account for the falling edge of the set on the?
You don't care about this at all.
Okay.
It's you care about this because it's this is when the set was asserted. Remember, it's asserted low.
Oh, gotcha. Okay.
It's not a matter of rising or falling. Well, it is, but I mean, it's because this fell. That's when the set was asserted.
Same thing if it was asserted high.
Yeah, it's just the opposite.
Okay, gotcha.
That's what it looked like here. We asserted it here when it went up.
Mhm.
Asserted it here. But if it's active low, it's going to be asserted when it goes down.
That makes sense.
Okay, I think with that should pretty well get it. I think this covers most of it. There are a few kind of common sense questions on there that you just should know from looking at the videos. You might want to, maybe peruse a few of the videos. I think I did some review videos online too. You should probably look at those. There's some extra review videos for midterm number 2. Should look at those. Yeah. They were specific for previous semester tests, but they're probably still helpful.
So are you going to have like the document that goes
Yeah,
along with the test?
It is, except in this case, you're gonna you have the option, you can click on a PDF or click on the Word file once you start the test. So you won't be able to see the document beforehand. Now, people that had Macintoshes, or one person with a Macintosh had problems seeing the Word document. So if you have a Mac, probably should do the PDF, but you can do both of them if you want, but the documents should be the same. But one of the documents looked like gobbledygook when the guy with the Mac clicked on it. So it was a problem. Okay, doke.
Sounds good. Thank you.
All right. Okay, guys. Good luck.
Thanks, Professor.
If you have problems starting the test or anything, let me know. Text me or send me I may not see the email, so you should text me. If you have a lot to explain, then put it in the email and tell me you email me in your text and I'll try and pull it up. Yeah, I'll be in micro lab during part of the day, and yeah, and I'll be actually in class. I'll be in class at 11, and then I'll be in lab on and off the rest of the day. But
Professor, can I ask you one quick question? So
Sure.
to go from POS to NOR, you can only do that using the theorem.
you can use a truth table to do it too. Well, no, yeah. Okay, sorry, I didn't answer that quite right. If you're in POS form and you want to go to NOR form,
Yes.
then you use De Morgan's laws and you do a double inversion, partially expand it, and you immediately, with a little bit of expansion of the first inversion, it puts you directly into NOR form if you do it right.
Dr.
right.
Morton,
Yeah,
quick question.
Sure.
So last time on the exam with the format, the questions were like parts of like all the questions, like mixed up, like number 7, part A, and
they'll
then
be the same.
okay, and then 5 questions later, you'd see like 8B or something like that.
Yeah.
So it's like, if we have a document, like how do you recommend we kind of solve the test? Like if we see a part of a question, should we go to that question and do all of it and then move on, or for next
Well,
time it comes up?
So when you first see the figures, like if you want to do the truth table and figure out the SOP and POS forms, you could just take your time to do that. Or you can wait till the question asks for that information, then you could develop it. Probably, I don't know, for some of the questions, it's better to wait till you're asked, because you may not be asked about everything. So you don't necessarily have to work everything out.
So you're not going to be posting that beforehand like you did last time?
No, you won't see it until you start the test.
Thank you.
Yeah, and it's randomized. The questions are randomized. Yeah, it's kind of about the only thing you can do to try and have some fairness, because it's really an open book test. But I just want you to, I want it work to be your own. But you can search the internet. You can you can look at the textbook. You can do whatever you want. But don't take a lot of time. If you're stuck on one problem and you burn all your time, researching that on the internet, looking for answers, then that may not be good use of your time. But I think if you followed the review today, then, and I will post I'll post the video here as soon as it's rendered, and I'll post it on Blackboard. And there's another video from the help session I did last year that's already on there. Maybe I think it's, well, I don't know. Anyway, it's on there somewhere. Yep. Okay.
Thanks, Professor.
All right. Good luck. We'll see. We'll
Thank you, sir.
see you later. Okay. I'll